When this video ends, you will look at your plant floor differently. Not because I told you what to think, because the data was always telling you. And now you'll know how to read it. Reventis, plant intelligence, delivered. Let's get into it.
Have you ever been in a meeting where IT person and OT person are trying to figure out why the two systems can't talk with each other? The simple answer is OPC-UA. Let me show you the problem first. Look at the left side of the slide. This is the presence in most plants today. Siemens PLC speaks Profinet. Your Allen Bradley speaks Ethernet IP. Your ABB DCS speaks Modbus. Each vendor builds their own language. They don't natively talk to each other. So every new system integration means custom code, months of work, expensive, and it breaks every time there is a firmware update. Now look at the right side. OPC-UA sits just above all of them. One protocol layer, all your PLC connect to one OPC-UA server. That server presents one unified namespace to your AI platform, your cloud, your MES, your ERP. You write the integration once, every system speaks to one layer. But here is the part that most people miss out about OPC-UA, and it's the part that makes the real difference for AI. It is not just communication protocol, it is a semantic protocol. In traditional system, a historian tag might just be called TT204. That's it, a number. The historian records it faithfully, but when you feed that to an AI model, the model has no idea what TT204 is. Is it a temperature, pressure, Celsius or Fahrenheit, line 3 or line 7? Nobody documented it. The model can't reason about it. With OPC-UA, the data carries its own meaning. The tag doesn't say TT204, it says that I am the inlet temperature sensor on pump P204 in building 3. I measure degree Celsius, my normal operating range is 65 to 85 degree. That context travels with the data everywhere it goes. That is the difference between data and intelligence, and that is why OPC-UA is the foundation that makes industrial AI actually work in practice. 3 reasons it wins. Security built in from ground up, designed for OT environment, not adapted from IT. I want to walk you through exactly what happens between a sensor reading a value on a motor and an alert appearing on a dashboard saying that motor will fail in 19 days. Because this journey from raw data to prediction is treated like a black box by most vendors. Data goes in, AI magic happens, prediction comes out. That black box framing is what makes industrial AI feel inaccessible. So let's open the box. There are 5 stages. I will use Vardhan line as an example, line 3 motor. The physical world meets the digital world. Your PLC or SCADA reads sensor values, vibration, temperature, pressure, current via OPC-UA gateway. Vardhan had 847 tags across 8 lines reading at 1 second interval. Every second nearly 1,000 data points. That's the raw material. Stage 2. All of that data goes into industrial historian. It may be OSIPy, InfluxDB, Azure Data Explorer, purpose built for high frequency industrial time series data. Vardhan, 3 years of data, approximately 2 terabytes, sitting in an existing Pi historian. Already there, already captured, just not yet utilized intelligently. Stage 3. Contextualize. This stage is in most organization is getting skipped and then wonders why their model don't perform. Contextualization means adding metadata that makes the raw data more meaningful. Which asset does this tag belong to? What does it measure? What normal operating range is? Vardhan, historian tags links to SAP Equipment Master, the first real OT-IT integration. The moment data stopped being numbers and data started becoming an information. This is where you derive new features from raw reading, rolling averages, rate of change, frequency component from FFT analysis, statistical measures across time windows. Stage 5. The ML model runs against the engineered feature stream in the real time. It scores incoming data continuously, looking for the pattern that matches historical failure event. And in Vardhan case, after the pipeline was built correctly, after labeling was done and after the model was trained, line 3 motor bearing failure was predicted within 18 days of lead time. 18 days. From a sensor reading through 4 transformation stages to a specific actionable prediction with nearly 3 weeks of warning. That's not magic, that's engineering, and now you understand every stage of it. Let's move to the data problem. I want to tell you about something that I don't talk about publicly very often, but that I think is important for you to hear before you go any further into your AI journey. I was a part of a program, a large transformation program, 100 crore rupees of investment that stalled for 18 months. Not because technology didn't work, not because the budget ran out, because 4 data problems that nobody had addressed before the AI work began. I'm giving you these 4 problems right now before you build anything, so you don't have to have a difficult conversation with your leadership. Problem 1, the labeling problem. You have the sensor data, you might have years of it, but you have no systematic record of when the failure actually occurred. No record of which data point preceded a bearing failure on line 3. No record of which reading correlated with a quality defect. Your machine learning model needs to learn the difference between normal operation and precursor to failure. But to do that, it needs labeled example of both. If your failure events aren't documented in a way that can be connected to your sensor data, your model has no target to learn from. It's like asking someone to to identify a disease from a medical scan without ever showing them a scan that has been diagnosed. Do you think it is possible? The fix is simple, and sooner you start the better. Every failure event in your CMMS from today forward must be recorded with a timestamp accurate enough to connect to your sensor data. Not just motor failed, but when, which asset, what was the failure mode, whether it was a genuine failure or a planned replacement. Then comes the problem 2, which is latency mismatch. Your OT systems capture data every second. Your analytic platform processes data every 15 minutes. So you see the mismatch, failure precursor window. The specific pattern of sensor reading that data appears just before a failure event. Might be 30 seconds long. By the time your analytic platform runs it in the next batch, that window is gone. So the fix is, define your required prediction lead time first. How many days of warning do you need to schedule a planned repair? Then design your pipeline latency to match the failure window, not the other way around. I already described it, the tag number TT204. So coming back to the same case, your historian has tag TT204. Your AI model gets fed TT204 as a number, a time series of values with no meanings attached. The model doesn't know its temperature, doesn't know it's from pump P204. Without that context, model treats TT204 the same way it treats every other numerical series. So this is the semantic tagging work I mentioned in OPC-UA lecture. Every tag needs asset ID, location, parameter type, engineering unit as minimum. It's a tedious work. Yeah, it's definitely tedious. It's not an exciting thing, but it's the work that makes the difference between a model that works and one that doesn't work. Now let's move to the last problem, shadow historian. This is one of the most human of the 4 problems. Your operators don't trust official data system. Maybe it went down during a critical shift once. Maybe the data doesn't match what they see on the machine. So they started keeping their own records on an Excel spreadsheet, on the line supervisor's laptop, a paper logbook in maintenance bay, a WhatsApp group where they share observation. These shadow systems exist in almost every plant. The fix isn't technical, it's cultural. You involve the operator in designing the data system. You ask them what they track, why. You build the official system around that, not around what IT thinks they need. 4 problems, all fixable, none of them requires new technology, all of them require someone to take ownership and drive the work.
If you want the complete framework, the full system, it's in my structured Udemy course. From first principles to live case studies. Link is in the description below. If this helped, like, share and subscribe to Reventis. Plant Intelligence Delivered. See you next time.